And now let's just sort of talk through this last step in the proof. So up until this point, what we've successfully done is we've demonstrated that we took the two angle bisectors at A and at B. So let me sketch those on here real quick. The angle bisector from A and the angle bisector from B. We sketched those two in. We know that there's a single point at which those two meet because they're not parallel lines. And then our job was to show that that point of intersection, if we connect it with the third vertex C, bisects that angle at C. So we needed to show that those two phi's that are on the author's diagram are congruent. And we did that by chasing around some congruent triangles. And we started the chasing by dropping a perpendicular from the point at K to the side BC, and then also to the side AB. And then lastly, we also did it to the side AC. So we drew in these perpendiculars. Perpendicular, perpendicular, perpendicular. And then using angle-side angle arguments, we got as far as demonstrating that all three, I'll put triple marks in here because that's what we had in the diagram on the board, that all three of those segments from K, the point of intersection of the first pair of angle bisectors, out to the three sides are all congruent to one another. But what we haven't yet done is established that this final set of two triangles, so KFC and KEC, we haven't finished demonstrating that that set of triangles are congruent. We can do so if we can use an SSA congruency criterion. So when we get down to the final part of this proof, ASA isn't enough anymore because that side which we know is congruent is not the side which joins our two corresponding angles. Instead, we have two connecting sides and then an angle which is only adjacent to one of those sides to work with. So we have SSA. And it's worth thinking about whether SSA is actually a congruence criterion, or whether it's possible to have a triangle so a pair of triangles in which they have two congruent sides and an angle which is adjacent to only one of those sides which are congruent, but have those triangles be not congruent to one another. And so where I'm going to leave this, the cliffhanger I'm going to leave this, is that we can use an SSA criterion, but we need to know something else. We need to know one more thing. And that one more thing is explained by how this criterion is actually named in Chapter 1. It's not named SSA, it's named SSA+. So look back into Theorem... So Theorem 1.4.2 provides us with a restricted SSA congruence criterion, but it requires us to know one more thing about the angle A. In particular, we need to know why the angle A is the biggest angle in the triangle. If we can show the A that we're using is the biggest angle in the triangle, then we can use SS with that A to establish congruence. So then the last question is, how do we know that this A that we're using is the biggest angle in these triangles?
It's the hypotenuse.
Because it's a 90-degree angle opposite the hypotenuse, and what do we know about the hypotenuse in a right triangle? It's the longest side. And why is the longest side opposite the biggest angle? We called it. Again, it's Sabrina's theorem. It's the Rizzo theorem. Theorem 1.2.9, the angle side inequality. Right, exactly. So that's the denouement of this proof, and it pulls into a new congruence criterion we haven't had to use before.